I've talked a lot about quantum hype, but I only recently saw that some news outlets are now giving investment advice for what quantum tech to buy stocks of. I want to talk about this because I don't want you to lose your money. We have here, for example, US news that says that many investors are missing the boat on the next massive technology breakthrough, quantum computing, and that the technology's growth rate is impressive. Then they tell you to buy Microsoft stocks. It's funny that while Microsoft has a quantum computing program, it's comparably small and has been going very slowly. So, if you want to invest into Microsoft, by all means, go ahead. But don't do it because of their quantum computing. It's like buying an e-bike because you like the bell. But is it actually true that the growth rate is impressive? Well, here's another website which claims that the quantum computing market is supposed to increase to 5.3 billion by 2029. Really? What do they want to sell? Schrödinger's cat calendars? They want what, $5,000 for their report? Well, at least these people have found a way to make money from quantum computing. Then we have this website called Fool.com, which says that quantum computing is exciting because this field of research promises to accelerate computing speed by an order of magnitude greater than what's possible today. I've no idea what that means. Actually, I'm not sure it's even grammatically correct. Then they ask you to buy stocks from IonQ. This is also funny because the IonQ stocks have been dropping for the past year. The company IonQ, as the name suggests, uses ion traps as qubits. As I've said in several previous videos, I don't think these are going anywhere because the traps are quite slow to react, much slower than superconducting circuits, and they scale badly because of their geometry that usually has the ions lined up in one dimension. One-dimensional thinking. As someone who spends most of their time looking at the research on the topic, I understand the excitement, but I don't understand how anyone can think there's money to be made with it anytime soon. My best guess for what's happening is that people get confused by all those crazy headlines. Here are just a few examples I came across this week. The Japanese telecommunication company NPP, for example, supposedly deploys quantum computers to improve their phone service. Which quantum computers? We don't actually have quantum computers that do anything useful. So what magic is going on in Japan? I suspect this is a misunderstanding. NPP has been doing very interesting research about quantum algorithms. Quantum algorithms tell you how to work with superpositions and entanglement on a quantum computer to get a desired result. But you can simulate quantum bits on a conventional computer. If you do that, you do not get the speed advantage that you'd get from a quantum computer, but you can use the algorithm nevertheless. And it might be an algorithm you hadn't previously thought of. This is sometimes called a quantum-inspired algorithm. It seems to me that NPP is using such a quantum-inspired algorithm, so they're not actually using quantum computers. This headline isn't just misleading, it's actually wrong. Look, if you bought a ticket for a Taylor Swift concert and instead you got a Taylor Swift-inspired artist, wouldn't you be a bit disappointed? Then we have this other recent headline according to which Lufthansa says that quantum algorithms for airport operations are ready for takeoff. Alas, the only thing taking off is my eyebrows as they rise in disbelief. Because, again, they're not actually using quantum computers. This is just an announcement that they've partnered up with a university to develop an algorithm that might run on a quantum computer one day, maybe. Then we have a recent McKinsey report. To get this report, I had to sign up for their newsletter with a burner account. I hope you appreciate my pain, but at least they didn't ask for money. The McKinsey report says there's lots of progress in quantum computing because, for example, Alice and Bob, that's a company, demonstrated 100 highly reliable logical qubits using just 1,500 cat qubits. Wow! How could I possibly have missed this? This is big! Well, if you look at the paper, they demonstrated that this could work theoretically. They haven't actually done it. Don't get me wrong, this is all very nice research for a theoretical physicist like me, but there's very little practical progress. I won't give you advice on what stocks to buy, but I would advise you to be very, very careful with news about quantum computing. They're 95% bullshit. But you might want to invest in my new quantum startup. Your stocks won't actually drop until you look at them. I just love talking about things that climate scientists don't want to talk about. And today I have a fun example. There's a little secret hidden in this figure. Raise your hand if you've seen it before. 1, 2. Is that a raised hand, or are you looking for a cell phone signal? Well, not so many it seems, so let me start with a figure that most of you have probably seen, namely this one. This is the projection for the expected temperature increase from continued fossil fuel emissions. It comes from the most recent IPCC report, and it shows the projections for several different ways the future could play out. The shaded areas and the bars on the right are the uncertainty ranges. The way that they do this projection is that they collect calculations from about 24 of the best climate models. Then they calculate the mean value and a deviation from the mean value. This figure then shows the simulations for the temperature in the past from different models. Each of these squiggly lines here is a different climate model, the rainbow of scientific uncertainty, so to speak. The fat red line is the mean value of the models, and the fat black line is the data. If you want to look for your favorite color, here's the list of models. The relevant bit that I want to draw your attention to is the vertical axis. As you've probably noticed, climate scientists usually don't tell you the actual temperature. They tell you a temperature anomaly. That's the deviation from a baseline. Unfortunately, the baseline can change from one figure to the next, and as we just saw in an earlier video, this can get a bit confusing. So why do they do this in the first place? Why not just use the absolute temperature? Very good question, thanks for asking. It's not that the models don't predict absolute temperatures. Climate models take in data about how much energy we get from the sun and how much the surface and atmosphere retain, and that gives you an absolute temperature. The issue is that they predict wildly different temperatures, and most of them are way off the observations. This is hidden in this figure on the right side here. See that it has an absolute temperature scale, and these thin lines here, those are the absolute temperatures for the different models. As you can see, they differ by as much as 3 degrees. That's more than the total warming over this entire period. The reason climate scientists talk about the temperature relative to a baseline is that their models are really bad at getting absolute temperatures right, though maybe they're also a bit jealous of Einstein's special relativity. What does this mean? There's nothing wrong in principle with separating the slope of a curve from its offset, so I'm not saying there's something fishy going on here. But that the models disagree so much about the absolute temperature tells you that there's something not quite right about the physical basis of these models. And I don't like that at all. In my mission as chief complainer, I also want to mention that they're using a very odd way of calculating uncertainty in these projections, because each model on its own has an uncertainty already, which is missing here. It's missing because they don't know what it is. None of what I just told you is news to climate scientists. They know this full well, at least I hope they do. But I don't like it that they don't mention it. The reason this bothers me is that downplaying the shortcoming of the models leads people to underestimate the risk of delaying the energy transition. Because just look at all those net zero plans that countries are making. They all rely on this mean estimate. But it might be that the reality is far worse, and you'd think that we have a plan for this as well, which, well, we don't. When I was young, I used to think adults have plans for everything that's important. They know what they're doing. Then you grow up and you realize that no one has any idea what they're doing, and also you're an adult now and are supposed to be doing something. Awkward. It's like being promoted to captain of a ship that's already halfway underwater. and the best I can think of is to make a video about it. I've tried to understand why so many humans are worried that AI will come and kill us, even though I've said they won't do that anytime soon. Why is it that not everyone agrees with me? I find that hard to understand. Then I've noticed that a lot of these fears aren't about AI, they're about robots. In my quest to comprehend the workings of the human mind, I've therefore deduced that humans probably think that AI could use robots to come and kill them. Because as long as AI is just software running on a computer, well, one could just pull the plug and be done with it. But what if they have robots walking around that put the plug back in? Oh no! Sounds bad indeed, but wait a moment. If robots are as good at moving around as you see in these footages, where are they? Why don't we all have robots already? Are they hiding something from us? Is NASA building a robot army behind the ice wall at the South Pole? Are these robots really just humans in disguise? I don't think so. It's rather that these impressive videos don't tell you the whole story. There are two big reasons why we don't have robots everywhere yet. The first is that it takes a lot of data to train an AI, and there just isn't remotely enough data to train a robot to perform well in an everyday environment. Yes, you can try to use video recordings, but there's only so much of that which helps the robot, and also it's two-dimensional. Yes, you can just let them learn from trial and error, but that takes a very long time, and then the robots only know one very specific environment. Yes, you can train them in a virtual environment, and companies like Boston Robotics do this a lot. However, you get to a point where creating a more physically realistic virtual environment becomes even more labor-intensive than just finding examples in the real world. What you see in these impressive videos are examples of where a robot was specifically designed for a specific task and specifically trained on that very task for a long time in that exact place. I strongly doubt that Atlas from Boston Robotics would be able to jump around that impressively elsewhere. But suppose you wanted to roll out a household robot. That robot would need to understand doors and carpets and cupboards and fridges and everything in those cupboards and fridges, and what to do with them and how to handle them under all possible circumstances. But there isn't any training data for it. What some companies have done instead is, for example, to just recruit people to move around their house and doing normal tasks with a tracking device that collects data. But this doesn't get you far because, again, it's just very little data. DeepMind also has called into existence an initiative called OpenX Embodiment Collaboration that collects data from different robots to be used as training for others. But still, this doesn't bring together any sizable amounts of data. You'd need an army of 1 billion robots just to train robots. It's not that I want to belittle the progress in robotics. It's really amazing, and I'd love to have a robot cat. But this progress is much, much narrower than it looks. This is also why I don't talk about robot news anymore, because they're too super specific. We're waiting for 3CPO, but get a robot arm that can put sushi on a plate. So this is the one big obstacle on the way to the robot revolution, the lack of training data. The other issue is that robot hardware is still really, really expensive. For example, this robot hand from Shadow Robotics costs about 110,000 euros. Just the hand. They say on their website that generally you can expect something like 10,000 euro per degree of freedom. So any humanoid robot will easily cost a few 100,000 euros and up. Why is it so expensive? It's mostly because there's still an enormous amount of labor that goes into the manufacturing. And this high cost creates a friction in the industry that slows things down a lot. This is why I was saying in a recent video that the intelligence explosion won't work the way that guys like Kurzweil and Aschenbrenner seem to think it'll work. It's because economic and physical reality gets in the way. Their intelligence explosion requires data about the real world. That data, they say, will be collected by robots. But to train your robots, you need the data already. This is why I think robots won't come to take over the planet anytime soon. That said, I think it's likely that robot AIs will be the first to acquire some level of consciousness. It's because I believe the key ingredients of consciousness are the ability to create a predictive model of your environment and to self-monitor. Current large language models have no use for either, so they have no reason to become conscious. But robots have use for both ingredients of consciousness, and they already use both, if in very limited form. This is why I think that if you want consciousness, robots are the way to go. If you want intelligence, use AI. Let me know in the comments in case you want me to expand or if you're fed up with this already. I find humans a little hard to understand. The other day, someone sent me a link to a video about fossil fuels not being fossil fuels, asking what this is all about. I clicked on it and it turned out to be Tucker Carlson interviewing a climate change denier. I've had a look. Since I found out the other day that my husband has never heard of Tucker Carlson, Tucker is a conservative American commentator who used to work for Fox News until one day he didn't work for Fox News anymore. You see, even Fox News now admits that climate change is real, sometimes. So Tucker is now distributing his wisdom on his own, for example, on YouTube. In this video, he interviews Dr. Willie Soon, an astrophysicist who doesn't think that climate change is caused by humans. Why is it always physicists? The interview starts out with Dr. Soon explaining to Tucker that not all hydrocarbons come from fossils. Tucker thinks this is a big deal and is very surprised, or at least he's very good at pretending he's surprised.
It's kind of incredible because all of us, and including myself until very recently, assumed that all of our main energy sources are these so-called fossil fuels, and of course their existence is going to be limited by the amount of fossils, by the amount of decaying organic material.
Not so.
So if that's not so, then we need to rethink a lot of things. If we haven't been told the truth about where hydrocarbons come from, and we haven't, I mean, I've never met a single person in my life who said, wait a second, they're not all fossil fuels, then we keep hearing there's a scientific consensus on climate change. Every scientist believes the same thing about it, believes Al Gore and John Kerry. Maybe that's not true either.
So what's this all about? Hydrocarbons are molecules that contain both hydrogen and carbon. It's the stuff that we burn to generate energy: methane, propane, oil, coal, and so on. We usually refer to those as fossil fuels because they come from fossils, dead plants mostly, that have been buried under sediments for a long time and created these molecules over millions of years. Under pressure. That said, hydrocarbons can of course be created in other ways. It isn't all that difficult, for example, to synthetically produce propane or kerosene, though that, of course, requires energy. Hydrocarbons are basically chemical energy storage, which is what makes them so useful. What Dr. Soon is going on about in the interview is that some hydrocarbons on Earth are produced by geological processes and not biological processes. These hydrocarbons are then called abiogenic. The abiogenic petroleum theory has it that the mantle of Earth actually has a lot of methane and oil that didn't come from fossils, but it's buried much deeper underground than that coming from fossils. Someone rediscovers this theory every couple of years, and every time that happens, people are surprised about it. Scientists are not particularly convinced by this idea. Yes, it is indeed possible to create hydrocarbons from some chemical reactions of water with rocks under sufficient pressure. The simpler the molecule is, the easier this can happen. The simplest abiogenic hydrocarbon is methane. But that said, there are various ways that we know the hydrocarbons that we've dug out of the ground are almost exclusively from fossils. First, there's the ratio of carbon isotopes. Plants preferentially take up the lighter of two carbon isotopes from the atmosphere. So if you measure the isotope ratio, you can find out whether the stuff came from dead plants. This is also how we know that most of the carbon dioxide we have added to the atmosphere came from fossil fuels. There are two other reasons we know that most oil and gas comes from fossils. One is their composition. They're usually mixtures of different hydrocarbons with some impurities. You expect that from fossils, you don't expect this from abiogenic processes. And then there are the locations where we find them. That's in places where plants sunk into the ground and rotted away. Taken together, there's little doubt that most hydrocarbons that we've dug up so far come from fossils. There are some exceptions to this. For example, there are pockets of methane below the ocean beds. Some of these, geologists believe, were formed by chemical reactions with rocks at high pressure. But it's the exception rather than the rule. None of this means that there couldn't be many more abiogenic hydrocarbons deeper down in Earth. This is, I think, why this idea appeals to a lot of people, because it'd mean that peak oil is way off, and also there's a lot of money to be made. But the fact is that no one has found these supposed abiogenic petroleum deposits. And if finding them takes a lot of deep drilling, then, why not just use geothermal energy instead of oil? Dr. Soon seems to have forgotten to mention these additional details in his explanation to Tucker Carlson. The interview then continues as follows.
So why don't most people know this? Why do most people think that the gasoline in their car was, by definition,
have to be limited?
Yeah, that there's just a tiny amount and it's going away. We'll never find more.
The world is full of untruth and half-truths, right? That's the whole problem, right?
So after feeding Tucker Carlson a lot of half-truths about abiogenic hydrocarbons, he complains about half-truths and concludes that climate change is a hoax.
What's that, brother?
This video comes with a quiz that lets you check how much you remember. The video's titled, "This is what they don't want you to know about the climate agenda." But the question of whether fossil fuels are really from fossils doesn't really matter to their impact on the climate. That's because where light absorption is concerned, carbon dioxide is carbon dioxide is carbon dioxide. Actually, if a lot of the hydrocarbons that we have already burned were abiogenic in origin, which they are not, that'd be worse. Because if they come from fossils, then we know that all this carbon dioxide was already in the atmosphere previously, and at least some forms of life survived that. If that wasn't the case, God knows what's to come. The brief summary is that, yes, hydrocarbons in the Earth's crust can come from other sources than fossils, in which case they're called abiogenic. We've known this for half a century. However, the hydrocarbons that we've dug up so far almost all come from fossils. We can tell from their isotope ratio, composition and location. Whether there are more abiogenic hydrocarbons deeper down is unclear, but if there are, it would be a very good idea to leave them there. Dr. Soon then dishes up some old-school denier arguments like the "it's all natural variability" idea.
But that other factors, the orbits, plus the changes of the sun by itself, between how bright, how dim it is, these two factors can explain just about everything that we know. All the data that I have.
No, we know that the current temperature increase does not come from changes in solar energy, because that'd warm up both the surface of our planet as well as the upper atmosphere. Whereas warming caused by an increase in carbon dioxide warms the surface but cools the upper atmosphere. And the upper atmosphere has indeed been cooling. I'm pretty sure that Dr. Soon knows that. He probably just expects that Carlson doesn't know it. It's another classical denier move. Soon then goes on to complain about how climate scientists reacted to the opening statement from Al Jaber at the COP meeting earlier this year.
I mean, in the beginning of this COP28 meeting, the chairman, or this guy from UAE, United Arab Emirates, the chairman, I don't know his name, Sultan Al Jaber or something, he was saying that there's no scientific reasoning to say that we should phase out fossil fuels. He's right. But then he backed off because of all this Everybody's like herd mentality. Everybody's doing the mad thing.
Unfortunately, on this, Dr. Soon is entirely right. There's no science behind a fossil fuel phase-out, because the problem isn't fossil fuel. The problem is climate change caused primarily by carbon dioxide and, to a lesser extent, methane in the atmosphere. Of course, the primary source of that is currently fossil fuels, but if the fossil fuel industry can find a way to avoid carbon dioxide emissions, which is a pretty big if, then that'd solve the problem. Now, as I've said previously, I don't believe that this is actually going to happen for various reasons, but that's another story. The story here is that Al-Jaber's statement was entirely correct. The problem isn't fossil fuels per se. The problem is climate change, and we shouldn't lose the goal out of sight. What's happened, however, is that a lot of climate scientists have declared the fossil fuel industry an enemy. This isn't about science anymore. It's a political movement that's conflating science with politics. I made a video about this earlier this year, and of course my comments were full of people claiming I get paid by the fossil fuel industry. It's a classical ad hominem attack directed at me, not the substance of what I say. Though it's actually worse than that. So let me tell you something I only found out after I published the video in January. In that video, I was quoting a climate scientist at the University of Oxford. His name is Miles Allen. I don't know him personally, but he's the guy who coined the term net zero and who launched the idea of extreme event attribution. So in my earlier video, I had a quote from him that I took from a UK website called the Science Media Centre. They collect quotes from scientists on topics of current interest and make them available to journalists. It's actually a really good idea. The quote from Allen that I found there was, "It's depressing to see the climate establishment reacting so furiously to a perfectly accurate statement by the COP28 president. To limit warming even close to 1.5 degrees, we must both scale down the use of fossil fuels and scale up safe and permanent carbon dioxide disposal. It's simply not true that to stop global warming, we have to stop using fossil fuels. What we have to do is stop dumping the carbon dioxide they generate into the atmosphere." I use that quote because it's exactly what I was thinking, but he's a climate scientist and I'm not. So I thought it'd be good to have a quote from someone, who's a little more suit and tie than pink shirt and fuzzy hair. But when I went back to the website to take a screenshot, the quote was gone. This all happened while the COP meeting was still going on. I later learned from people who don't want to be quoted that several climate scientists gave Allen a hard time about that quote, and he decided to withdraw it. I don't know whether this is true, but it sounds plausible enough, doesn't it? In hindsight, I feel somewhat sorry for drawing attention to the quote, even after I saw that it had disappeared. But really, this isn't about Allen or Al-Jaber. It's just a vivid example that illustrates that the community of climate scientists is trying to enforce a narrative that they want their members to play along with. I'm not a climate scientist. I don't give a shit what they want me to say. And this is why you see so many complaints in my comments. People who accuse me of being funded by the fossil fuel industry every time I say something that doesn't agree with their narrative. I'm still waiting for my offers, people. More seriously, this is a huge problem. That a group develops and enforces a narrative that they require loyal members to conform to is one of the most obvious symptoms of groupthink, and the climate change community is very deep into this. It's bad for one thing because it discourages criticism and increases the risk of mistakes. It's also bad because people who are not in the group, like Dr. Soon and me, notice it, which creates a backlash. Why is it always physicists? So here's Sabine to climate scientists. Stop censoring your own people. And the rest of you, please check out my Patreon so I can continue to complain about Tucker Carlson. A few years back, I had a minor surgery. I was totally prepared for sharp instruments, but then the doctor gleefully showed me his new plasma scalpel. I've since noticed that plasma everything has become really trendy, including a plasma-powered nappy bin. What's up with all this plasma stuff? What even is plasma? Let's have a look. Plasma is often called the fourth state of matter, in addition to solid, liquid and gas. It's different from the other three in that in plasma, electrons are no longer bound to atomic nuclei. They're free-range electrons, basically. So a plasma always has two components, a positively charged one and a negatively charged one, and those can behave independently. In general, they even have two different temperatures, as if one temperature wasn't complicated enough. You have probably heard of plasma as what makes up the sun or what you have inside a nuclear fusion reactor. In these cases, the plasma is created through the heat and pressure that rips the electrons off the nuclei. But there are easier ways to create plasmas. For example, by pushing high voltage through gases. That'll also rip electrons off air molecules and, yes, create small amounts of plasma. Another fast and easy way to create a charged situation is asking a particle physicist why they still haven't found supersymmetry. What makes plasmas attractive from an engineering perspective is that charged particles can quite easily be accelerated and directed. This is why you can use plasmas to propel spacecraft. We just talked a few weeks ago about a small plasma thruster to maneuver spacecraft. It produces a thrust in the range of 40 or so millinewton. But the American company Howe Industries now wants to build a giant plasma thruster that can generate up to 100,000 newton. That's still not enough to get a rocket off the planet, but it'd be a lot of thrust once you're in space. Indeed, they say this could get you to Mars in as little as 3 months with small amounts of fuel and high efficiency. Personally, I think that's still more time than I'd like to spend locked up in a can floating through a vacuum. But then again, at the moment, getting to Mars takes about 9 months, so it'd be an improvement indeed. How do they want to generate that much thrust? With good old nuclear power. Nuclear fission power, to be more specific. A controlled chain reaction in uranium that evaporates a fuel pellet and heats it up dramatically very quickly. This could generate a lot of thrust because it'd produce a lot of plasma, so you'd have a lot of stuff that you can throw out of the spacecraft. You need the nuclear fission reaction to produce enough power to make that happen. NASA recently announced they'll be supporting the project. But this isn't the only thing you can do with plasma. Plasma applications can loosely be distinguished in 3 types, those that use hot, warm and cold plasma. Hot plasma is the nuclear fusion sort of stuff and what the rocket thrusters work with. The plasma scalpel uses warm plasma, that's usually a few hundred to a few thousand degrees Celsius or so. The big benefit of plasma scalpels is that they don't just cut, they pretty much immediately fuse blood vessels, which significantly reduces blood loss. At least that's what the doctor told me. Has anyone else noticed that doctors really like showing off their new tech? Hey, look at this amazing new tooth extractor. Okay, but I digress. The reason that plasma has become much more widely used in the past decade or so is because of technological advances that have made it possible to create cold plasmas quite easily in everyday circumstances. Cold plasmas have room temperature, that's the heavy particle temperature, so they don't burn stuff. However, because the components are so highly charged, cold plasmas still have rather dramatic effects on other materials. One of the obvious applications of cold plasma beams is precise etching of surfaces or depositing certain molecules on the surfaces. This is very useful in many industries. But the application that cold plasmas have become most widely used for is killing germs. They're being used to sterilize medical instruments or also surfaces, because that way you don't need to use chemicals. Cold plasmas can also be used to purify water or decontaminate air and to make food more durable. And this is also why there's this plasma nappy bin. The idea is that you put in your stinky trash, push the plasma button, and that'll kill off any bacteria that create the stink. At least that's the idea. I haven't tried the thing, though I now want to launch a startup for plasma-enhanced washing machines. The widespread application of cold plasmas is a recent development owing to technological advances in electrode quality and a better understanding of what these plasmas can do. I think this is a pretty interesting development, and I'm curious what uses for plasmas engineers will come up with next. I hope lightsabers are among them. As to that plasma scalpel, the smell was terrible. Definitely do not recommend. Thanks for watching. See you tomorrow.